Standard ways of data visualization use Cartesian planes. This is an effective way to display data. It gives us an easy way to identify relationships between variables, recognize broad patterns, and can be used as an effective communication tool. However, there is a very real limit to the amount of data that can be shown by a given data point. Let's start with the simplest example, a visual representation of one-dimensional data. Let's use the size of a sphere. For this, we can use a number line. The larger the number, the further it lies along the number line. Many data points can be plotted along this line, allowing instant visual comparison of the points. If we want to find the largest sphere, we simply look for the point furthest along the number line. What if we wanted to compare this to another property? Let's use the sphere's mass, for example. Again, we already have an established way of doing this. We create a second axis, perpendicular to our existing number line. Our existing points still take the same location along the size axis, but now also move along the mass axis. And thus, each point represents two values, the sphere's mass and its size. The further along we move along these axes, the heavier and larger the spheres are. This is still a very convenient and useful way of representing data. Let's say the spheres are also all at different temperatures. Now we have three data sets, size, mass, and temperature. We can repeat the same process we did before. We draw another axis perpendicular to the existing axes to allow the representation of the additional data set. This is now difficult to see on a flat sheet of paper, but using 3D graphics, we can navigate the graph quite well. Some data sets are a bit more difficult to see, but it's still a useful tool. We can find our hottest and coldest spheres, look at the size and mass distribution, and see if there's any correlation in the data. Here, we can see that there's a correlation between size and mass, which is a useful thing to know. The data here is successfully represented. We have reached a bit of a barrier. We can't continue in the same way for another dimension. There is no space to add another perpendicular line. Let's say our spheres have different levels of luminosity, and we want to communicate this on the plot. How can we do this? Well, the easiest way is to color the dots. Let's say the brighter spheres are closer to blue on the color scale, and the dimmer ones are closer to red. This allows us to compare between data points, but our ability to get actual values from the graph alone is diminished. However, it is still reasonably intuitive and doesn't detract from the rest of the data. But what now? What if we wanted to show how strong the sphere's magnetic field is, and how fast it's spinning, and show velocity, acceleration, electric resistance? Sure, we can add some different modifiers to the data points to increase the amount of data represented. We can change the size, shape, angle, or transparency to indicate different data values. But these features will not only be hard to read by themselves. When put into a graph, they take away from its usefulness. The graph becomes too cluttered and difficult to read. When seeking to represent multidimensional data, we clearly need another way. Data tables by themselves can be used, but they have some important drawbacks. They can't fit on one screen, and they provide weak visual clues. It's very difficult to see any patterns or structures in the data. Let's start again from our number line. When adding a second property, instead of drawing a second line perpendicular to the first axis, we draw it in parallel. Each dataset is not represented as a point on this graph, but as a line connecting corresponding values on the axes. The point of intersection with the axis corresponds to the value the sphere has in that dimension. This can easily be extended to 3 dimensions. Using this method, we can easily see direct and inverse relationships between data points and multiple variables. In fact, our entire dataset can be displayed using this method. We can also color the data lines according to the plotted dimensions to better see the relationship between the values. In this case, the lines are colored according to sphere temperature. Comparing axes, we can identify broad patterns, For example, we can see that the lines between the size and mass axes are roughly parallel. This shows a positive correlation between the two variables. That is to say, a larger sphere tends to be more massive. Comparing the magnetic field strength axis and the resistance axis, we can see the lines intersect each other. This intersection is due to an inverse relationship. The stronger the magnetic field, the weaker the resistance, and vice versa. We can also use parallel coordinates to isolate data. Let's say we are most interested in seeing what our data looks like when we are only dealing with the larger spheres. Well, by filtering out the smaller spheres, we can see strong positive correlations between size and mass, and size and resistance, and a strong inverse correlation with magnetic field strength.